Good evening, all of you. Today we are going to see the GATE Aerospace 2022 solution on aircraft structures subject. So first we will start from one more question. Yeah, sixth question. A beam is having a T cross section throughout the length, which is subjected to only pure bending. So here they are asking you to find out the maximum magnitude of normal stress. Maximum magnitude of normal stress they are asking. If you see the T section, your centroid will lie at this particular location. Okay, so this will act as a neutral axis. If you draw the bending stress distribution, say for example, the moment is acting towards upward direction. So the top layer is subjected to compression, bottom layer subjected to tension. This is the formula for finding out the bending stresses. M constant value because it is subjected to pure bending. I throughout the length uniform cross section. So moment of inertia is also constant. So the only variable is y. If I want to find the stress at this top layer, I'll be substituting this much y distance. If I want to find the bottom stress bending stress value, I'll be substituting this much y value. So if you see these two, here you'll be having maximum y value. So when you substitute this much y distance, you'll be getting the maximum magnitude of normal stress. Okay. So the bending stress distribution is here compression, here tension. So the distribution will come like this. So from this option, we can select B, only at the bottom fibers of the cross section. Okay. Now let us move to the next question. Yeah. So here you have a 3-member truss, which is subjected to only one force F towards right-hand side direction. Now we can draw the free body diagram for this. Q support is hinged support, so you'll be having two reactions. R is the roller support, so only vertical reaction will be there. Now, if you see this QR member, this is the question which they asked you. The force acting on the QR member, they are asking. Now, let me take Q, horizontal is equal to F. Now, let me take the joint Q. Okay, if you see this joint Q, here we have a horizontal reaction which is also equal to F. Then this side you have a member F QR. Okay, then here we have a vertical reaction at Q. Now if you see this, you can apply the horizontal equilibrium equation. So the value of QR is equal to F. Since we got the positive value, so the correct option is F, tensile. Okay, the member force on QR is equal to F, tension. Then next question. Yeah. The closed thin-walled rectangular channel section shown in figure is opened by introducing a sharp cut at the center of the bottom edge. So they gave you two diagrams. First diagram is completely closed. Okay. In our second diagram, they made a small cut over here. Okay. So in the first diagram, if you see which is symmetrical about y-axis as well as x-axis. So whenever a given section is symmetrical about x-axis as well as y-axis, this is the centroid. The centroid will coincide with the shear center. Okay, another concept which we have to remember is for a closed section, always the shear center will lie inside the cross section. But if you see any open section, say for example, this is a rectangular slit. Because you made a small cut over here. Okay, so the shear center will lie inside for a closed section. But if you take the open section, the shear center will lie outside the cross section. This is very, very important. Okay, but if you see the geometrical value, both are same. So the centroid will be the same. Say for example, since it is symmetrical about this y-axis, so our shear center may travel along this axis. Probably it will come over here based on its dimension. Okay, so two things you need to remember. One is for any closed section, our shear center will lie inside. For any open section, the shear center will lie outside. If any one axis symmetry exists, it will travel along that axis of symmetry. Okay. So in these two cases, our centroid is same, but shear center is not at the same location. So the correct option is A. Centroid of first and second coincide, but the shear center will not coincide. Okay. Then the next question. So here they gave sigma and tau, which represents normal stresses and shear stresses. The Mohr circle that may possibly represent the state of stress at a point in the beam of rectangular cross section under pure bending. So here they gave you one beam whose cross section is rectangular cross section. This is the cross section. This is the neutral layer. It is subjected to pure bending like this. When you substitute the pure bending on the beam, it will deform like this. Top layer subjected to compression, bottom layer subjected to tension. So the bending stress distribution will come like this: compression, tension. This is the neutral layer. If you take any one small element above the neutral layer, the stress is acting is compressive. But when you take any element below the neutral layer, their tensile stress will act. Okay. So now we can split like this. Below neutral layer, the loading condition is sigma x is equal to sigma. Sigma y will not exist. Tau xy is also 0. The same way, above neutral axis or neutral layer, sigma x is equal to minus. All the remaining stresses are 0. Now we have only uniaxial condition. Since we have a sigma x is positive, let me take horizontal axis as sigma axis, vertical axis as tau axis. Here I have sigma value. So this value sigma y is 0. Now I can bisect this. Then I'll draw the Mohr circle like this. Then for the above neutral axis, we have a compressive stress. This is tau, this is sigma. Negative value, sigma y is 0. Okay. So the diagram will come like this. One is positive, another one is negative. So from this we can choose two options that are called B as well as C. Okay. Both are uniaxial condition. Next question. An isotropic linear elastic material point under plane strain condition in xy plane always obeys what are the condition. So the here given plane is xy plane. So the out of plane is z direction. So you have to remember a few assumptions that are called zero strain values and zero stress values for plane strain condition. When you consider the strains out of plane, normal strain is 0, gamma x is at 0, gamma y is at 0. Out of plane shear strain 0. Then if you see the stress component, only tau x is at 0, tau y is at 0. Okay, sigma z is not equal to 0. This is very, very important. Okay, so now we need to choose the option accordingly. So let us take the first option, epsilon z 0. Yes, this is correct. Then see the second option, out of plane normal stress sigma zz is equal to 0. Yes, this is the wrong answer. Okay. Then out of plane shear stress is 0. This is also correct. Out of plane shear strain, this is also correct. So the options are A, C, D. These three options are correct options. Yeah. So here they have given one two-dimensional plane stress element, which is subjected to 2D stress state. This is x direction, 110 megapascal. Y direction, 30 megapascal. Then shear, 40 megapascal. Okay, you can use two formulas. You can choose any one. The stress transformation formula, sigma x cos square theta plus sigma y sin square theta plus 2 tau sin theta cos theta. Or otherwise, you can use this formula also, simplified formula after using the trigonometry relation. Sigma x plus y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau sin 2 theta. You can use any one formula. So here let me take this one. Here the sigma x value is 110 cos 45 square plus 30 sin 45 square plus 2 times of 40 sin 45 into cos 45. Okay, so sin 45 is equal to cos 45. 1 by root 2 will come. In all the cases, we have a square. If you see the last term, we have a sin 45 and cos 45. So here also we can consider it as a square term. Once you simplify everything, you will get 110 megapascal. Okay, after simplifying these things, 220 into 1 by root 2 whole square will come. So if you simplify it further, you will end up like this. Okay, so the answer is also in megapascal, 110. Let's move to the next question. Yeah. A horizontal load F is applied at a point R on a two-member truss as shown in figure. Both members are prismatic with the cross-sectional area A0 and made of a same material with Young's modulus. Then the horizontal displacement of R is how much? First, we need to find out the length of the member from this using a trigonometry relation. Since the angle is 45 degree on both sides, so both member will be having same length. Okay. If you find out sin 45 of this opposite by hypotenuse, So this PR, which is also equal to QR, is equal to root 2 times of L. Okay, so the member length is root 2 times of L. Now I can take this R joint. In R joint, the externally applied force is F, and the member force along this side is F RQ. This angle is 45 degree. The same way, this side also 45 degree RP. Here also 45 degree. Now we can go for a vertical equilibrium equation. We go for a vertical equilibrium equation. FRP sine component plus FRQ sine component is equal to 0. So we have a relation between these two. One is opposite to another one. After using this vertical equilibrium equation, we got the relation like this. Then the same way, we'll go for a horizontal equilibrium. FRQ cos component plus F. These two forces are acting towards right hand side, so I'm taking it as positive. Then FRQ, it is towards left hand side, cos 45, so 0. Now I can replace this over here. So already I have one more term over here. So 2 times of F. Sorry, this is RP. Yeah, this is RP. Now I can replace this as minus RP 2 times cos 45 is equal to yes. Now I want to find the FRP. FRP. Okay. Instead of this cos 45, I can consider it as 1 by root 2, and I can cancel this. It will come like this. So FRP is equal to F divided by root 2. Already we have a relation for finding FRQ. So let me write it here. Minus F by root 2. Now we found out the two member forces. Two member forces we found out. Now we can go for the simplified Castiglione's formula for determining the deflection. In this given problem, they are asking us to find out the horizontal displacement. At that point, we have a externally applied horizontal force itself. So we can use that force for finding the deflection. Otherwise, we will be going for a dummy force. So the general formula for finding the deflection is summation of forces, differentiation of force L by AE. So for your understanding, let us make one small tabular column. In exam, no need to make these things and all. Dou N by dou F, then N into dou N by dou F, L by A naught So first let me take the first member. First member is RQ member. RQ member whose length is root 2 L. Then the second member is RP member. This member is also having the length root 2 L. Okay. The member force on RQ is minus F by root 2. Minus F by root 2. Here F by root 2. The differentiation of member force with respect to F. Okay. So if I do partial derivative, I'll be getting minus 1 by root 2. Here 1 by root 2. Now we need to simplify this thing, and we need to fill up this table column. F divided by root 2L divided by 2 A naught and E. Okay. Similarly, here F by 2 root 2 L is the member length divided by A naught into E. Now I'll have to find out the total value. Okay. 2 times of F by 2 L root 2 by A naught E. 2 cancel. So the net deflection is equal to root 2 times of FL by A naught E. Okay. FL by A naught E. So the correct option is C. Now let us move to the next question. Yes. Given tip deflection and tip slope for a tip loaded cantilever of length L, NLQ. So some tips they have given. We have a cantilever beam whose length is L. For this condition, they gave tip deflection N L cube by 3EI and theta at the tip slope NL square by 2 times of EI. Okay. So EI is the flexural rigidity. Now, a cantilever PQ of a rectangular cross section is subjected to a transverse load F at its midpoint. Okay. Two cases are considered as shown in figure. In case 1, the end Q is free, and in the case 2, Q is simply supported. The ratio of the magnitude of maximum bending stress at P in case 1 to that of case 2. First, we will find out the tip deflection due to midpoint load on a first case. Okay. This is the loading diagram. Okay, L in L. For this, I'm going to use the moment area method. That will be simple. That's why I'm using this FL. So the centroid will lie over here, 1/3 from the larger side or 2/3 from the zero side. Okay. Now, from this, I can able to find out the deflection at the tip due to midpoint load on a cantilever beam. So the formula is area of a bending moment diagram divided by E into I into X bar. Okay. My aim is to determine the deflection at this particular point. So I'll have to use this much distance. Okay. This distance is L distance. This distance is 2/3 of L. Okay. Now let us find out tip deflection of case 1 is equal to area of the bending moment diagram. Area of the bending moment diagram of BH of B such FL. Okay. Then the distance this distance we need to use L plus 2L by 3. Okay, so if we simplify this, here 5L divided by 3 will be there, outside 1 by 2 is there. So if you simplify it further, 5 by 6 times of FL cube by EI. This is the answer for first case due to midpoint load. Okay, and in the same way we will do for second case. Here we can idealize this into two individual cases. At this Q end, they gave a simply supported. Okay, so this case I can idealize into two things. One like this, and like this. Okay. This is the reaction at Q. This is also equal to N. Now I can draw the bending moment like this. This is F, FL. This is from here to here L, another L, N. It will come upper side. 2L into N. 2L into N. Already we have one relation for cantilever beam with tip loading condition. I can use it here. Tip deflection due to midpoint load on cantilever beam is equal to tip deflection due to tip load. Okay, so because of this midpoint load, the beam will try to deform like this. Since we have a simply supported end, this will resist. Okay, so the net deflection will be 0. That is the reason we are equating this formula. Already we have a relation for tip deflection due to midpoint load. That is 5 by 6 FL cube by EI. 5 by 6 FL cube by EI. Then for this NL cube by 3 EI. That is for L length beam. Please listen. This is very, very important. Here, the tips they gave like L length. Okay, but in our case, we have a 2 times of L. So N into 2 times of L. So PL cube by 3 EI. EI we can cancel. Then L cube we can cancel it. So N is equal to this also you can cancel 8 to 16. So 5 by 16 times of F. Now we got the relationship between N and F. Okay. Now we know the formula for bending stress, that is My by I. In both cases, the beam cross section is same. Okay. So I value and Y value will be same for both cases. Okay. Now let me take first case. In our first case, the maximum bending moment is FL. Maximum bending moment is FL. So let me take the moment at P for first case is equal to FL. Therefore, the bending stress for first case will be FL. This is our moment, Y by I. The same way, if we do for case 2, the maximum bending moment MP, bending moment at P for second case is equal to, here we have two diagrams. One is upper side, another one is lower side. Okay. So we have to find the difference between these two. FL minus N into 2 times of L. Now already we have a relationship between N and F. N and F. So 5 by 16 times of F. 5 by 16 times of F into 2L. 8. 3 by 8 times of FL. From this, we can find out the bending stress due to the case 2. 3 by 8 FL. This is our moment, Y by I. The ratio which they asked here is 1 by 2. Case 1 divided by case 2. Case 1 divided by case 2. FL Y by I divided by 3 by 8 FL Y by I. We can cancel FLY and I also. Then the remaining is 8 by 3. 8 by 3 means 2.6667 will come. Let me take 2.67. I think 2 decimal. Oh, sorry, 1 decimal only they are asking. So 2.7. The ratio is 2.7. Now we'll move to the next question. A simply supported aluminum column of length 1 meter and rectangular cross section W into T is subjected to axial compressive loading. Here the Young's model is 70 gigapascal. Yield stress under uniaxial compression is 120 megapascal. The value of T at which the failure load for yielding and buckling coincide is equal to how much mm? So here the type of column is simply supported column. So let us draw the diagram like this. This is subjected to axial compressive force. The length of the column is 1 meter. The condition is simply supported condition, which is also equal to hinge condition. The formula for finding the crippling load is pi square EI by L square, LE square. So here the effective length is equal to L only. So pi square EI by L square. We can find out the crippling stress like this. Here the area is W into T. W into T into L square. So whenever you are using this formula, you need to remember like always I value should be least value, least moment of inertia only you need to use. Okay. So let me simplify it further. I think here I missed 2. Pi square E. Instead of this I can put W T cube by 12. BD cube by 12, that formula. WT into L square. I can cancel W. I can cancel 1T from here. And the rest of the values I can substitute. Sigma CR. This is also equal to uniaxial compression yield strength. Okay. Here I'm thinking to follow all the dimensions are in meter. So 120 megapascal, right? So 120 into 10 power 6 is equal to pi square into 70 into 10 power 9 into t square divided by 12 divided by length is 1 only. So if we simplify, our t value 0.04565. This is in meter. The question is they asked us in mm. Okay. So our t value is 45.65 mm. 45.65 mm. So this is how we need to simplify this problem. Next question. A 0.5 meter long thin-walled circular shaft of radius 2 centimeter is to be designed for an axial load of 7.4 kilonewton and torque of 148 newton meter applied at its tip as shown in figure. The allowable stress under uniaxial tension is 100 megapascal. Using maximum principal stress criterion, the minimum thickness T of the shaft which do not fail is how much? Okay. So here they are asking you to use the ranking failure theory, that is maximum principal stress theory. If you look at the structure which is subjected to uniaxial tension as well as torsion. Okay. Let me take the cases individually. Here 7.4 kilonewton is acting. If you take the element over here, the stresses will act like this. Since it is uniaxial tension, I can use the formula sigma is equal to P by A. X direction. Longitudinal direction, I am taking it as X. 7.4 kilonewton, right? So 10 power 3 I am using. So this is thin-walled circular shaft. The area 2 pi RT you have to use 2 pi RT. If we simplify this, here your R value is how much? 2 centimeter. Yes. 7.4 10 power 3 2 pi R value is 0.02. I am substituting in meter. Let me simplify this. .89 into 10 power 3 divided by T. So if you look this case, only sigma x is acting, sigma y is 0. Okay. Then if you go for the torsional case, end torque case, 148 Newton meter. If you take any one small element over here, which will be subjected to pure shear, okay, it will look like this. Then we can use the formula, torsion formula, T by J is equal to tau by R. My aim is to determine the tau value. 148 is the torque into R. The polar moment of inertia of a thin-walled circular shaft is 2 pi R cube T. Okay. Now I can cancel 1 R from this. Now let me substitute the remaining things. 148 2 pi 0.02 meter into thickness. We'll simplify this. Here also the same value is coming, 58.89 divided by T into 10 power 3. So the theory which they are saying is maximum principal stress theory. Okay, so we'll have to find out the maximum principal stress first. We all know the principal stress formula, sigma 1 comma 2 formula, right? Sigma x plus sigma y by 2 plus or minus sigma x minus sigma y by 2 whole square plus tau xy square. So in this problem, y component y component is not there, so we can eliminate this. Then we have to substitute the sigma x value and tau xy value. These two values are looking same, so we can take it outside. Let me take only the first maximum principal stress alone. Okay, if we take this 58.89 into 10 power 3 divided by T. Here we have 1 by 2 plus under the root we have 1 by 2 plus 1 square. Okay, these are the remaining things. Now we will simplify further. (95.29 into 10 power 3 divided by thickness). So according to maximum principal stress theory, whenever the maximum principal stress of a complex loading system reaches the critical value is 100 megapascal here. Okay, critical value 100 megapascal. So we have to find out the thickness for critical value. Since I am following all the data in meter and Newton, so 100 into 10 power 6 I am using. Now we'll have to simplify this. Okay, so after simplifying this, I got like meter. The answer is in mm, that to nearest integer. Okay, that to nearest integer. 95 mm is coming. Nearest in the integer, so 1 mm. This is our answer. Now let us move to the next question. Question number 60. A 10 kilonewton axial load is applied eccentrically on a rod of square cross section 1 centimeter by 1 centimeter as shown in figure. The strains measured by two strain gauges attached on the top and bottom surfaces at a distance 0.5 meter from the tip are 0.0016, 0.0004 respectively. The eccentricity in loading E is equal to how much mm? Okay. So here you'll have to remember this condition. Whenever the force is acting at the centroid point, it will go for only elongation. If suppose this is the axis, but the force is acting over here means you need to idealize this case into two subcases. One is like this, like this. Tension and bending. Okay, so combined axial tension and bending cases, combination of these two cases. The same way here also we have to consider like that. The given case is looking like this. Since the force is acting above the dotted line, so it will go for a tension on top side and compression on bottom side. Okay. Now I can idealize these into two cases. This 10 kilonewton plus the eccentricity which we have here is E. So I can take this as moment, which is also equal to 10 into 10 power 3. That is the force into perpendicular distance. That is the E. Okay. Here top layer tension, bottom layer compression. For this case, if you draw the strain distribution or stress distribution, let me start with the stress distribution. It will come like this. It will vary in uniform manner because you are idealizing this condition. Okay, then if you come to the second condition, top layer subjected to tension, so it will come outside. Bottom layer subjected to compression, so it will go inside. Okay, this is tension, this is compression. Now, the same way, you can draw the strain distribution. Look this value. In first epsilon 1, you have 0.0016. Here you have 0.0004. Okay. For tensile condition, this is the tensile condition, first case. I can draw like this. The strain variation, I can draw like this. Initial value may look like this. Let me take it as only epsilon 001. Okay. Here, the epsilon value may be 0.0006. Here tension. Here 0.0006 compression. Okay. Now, if you add these two strain values, at top layer, already we have 0.0001. Here at top layer, we have 0.0006. So if you combine these two, you'll be getting 0.0016. The same way, if you look at the bottom side, we have 0.001. We have 0.000 in the opposite direction. Okay, so you will subtract this. Once you subtract, you will get epsilon 2 as 0.004. Okay. From this tensile condition, I can simplify like this. Sigma is equal to E epsilon. Here I can put P by A is equal to Young's modulus that I don't know. So I'm finding Young's modulus through this. 10 into 10 power 3. The cross-section area is 1 centimeter by 1 centimeter. Here I'm using in terms of meter. A square, okay. E into 0.001. From this, we can able to find out the Young's modulus. Let's simplify this. One into 10 power 11 Newton by meter square. I got the Young's modulus like this. Now we will go for a bending case. Sigma is equal to my by I. As we have seen earlier, you can simplify this formula further like E epsilon is equal to 10 into 10 power 3. 10 kilonewton force they have given, right? Into the eccentricity, this is our moment, into Y. 2 centimeter they gave, 1 centimeter they gave, right? So 0.01 divided by 2, half of the value. Then moment of inertia, a power 4 by 12. Okay. Now we have all the values. Young's modulus value is 1 into 10 power 11. Then strain value 0.00006. Yes, here 0.006 and at top and bottom. Okay. Magnitude wise both will be same. Is equal to 10 into 10 power 3 into E 0.01 divided by 2 divided by 0.01 power 4 by 12. Now we'll have to simplify this. Okay. So after simplifying, I got 10 power minus 3. Okay, that is equal to 1 mm. I think the answer is in mm only, I think. Yes, 1 mm. The eccentricity is 1 mm. If you want, you can cross check it. You use this in the bending equation and cross check it. Now let us move to the next question. 61 question. For a thin-walled high section, the width of two flanges as well as web height are same. That is 2b is equal to 20 mm. The thickness is 0.6 mm. The second moment of area about the horizontal axis passing through the centroid is how much? Okay. So the given section is symmetrical about both the axes. If you see the thin-walled structure, mostly they will mention the thickness from the mid side. Okay, they'll be marking the thickness from the mid side. But here they gave from this end to this end. Okay, better we can include half of the thickness on either side. If I do that, otherwise slight deviation will come. Now let us take like this. 0.3 I have to take on either side. So 20.6 mm will come. Here there won't be any changes. 20 mm. Okay. Here they're asking second moment of area, that is moment of inertia, about horizontal axis. X-axis Ixx is equal to, the formula is we have top flange and bottom flange, both will be having same value. So I'm using 2 times. The formula is bt cube by 12 plus a h bar square plus, this is for top and bottom flange. Okay, then b t cube by 12. Here I am not including a h bar square because the local centroid is going to coincide with the global centroid. Local centroid is going to coincide with the local centroid. Okay, global and local are coinciding. That's why I'm not using a h bar square term. So this is for web. For any thin-walled section, the thickness cube can be eliminated. Even if you are including, slight changes will be there. That's why we are neglecting it. Okay. So now we will bring this 2 inside and we will simplify. 2 into area of the flange, 20 into 0.6 into h bar square. H bar square is, okay, this is your global centroid. Here your local centroid will come. So distance between these two is 10.3 square plus p value is for the web 0.6 into height is 20.6 cube divided by 12. Now we will simplify this. (29.8325 mm power 4). Okay, the value is coming like this. Now we will move to the next question. A vibration question. A damper with damping constant C is attached to a mass 5 kg and spring stiffness of 5 kilonewton meter as shown in figure. The system undergoes underdamped oscillation. If the ratio of third amplitude to the fourth amplitude of oscillation is 1.5, the value of C is how much? So here the value they are asking in nearest integer. Okay. If you look this vibratory system, it is underdamped. So your zeta value will be less than 1. Okay. Then mass value 5 kg. Then stiffness value is 5 kilonewton meter. So whenever you are using stiffness value, you have to keep it in Newton meter. Okay. Newton meter. The question which they asked here is C value, that is damping constant. Then one more data they gave, the ratio of third amplitude to the fourth amplitude. So successive amplitude ratio they gave. X3 and X4 is equal to 1.5 times, 1.5. So through the successive amplitude ratio, we can able to find out the logarithmic decrement. Okay, we know the formula for finding the logarithmic decrement. Delta is equal to ln of x3 by x4. Here, this is successive amplitude. That's why we didn't use 1 by n outside. Okay. So ln 1.5. 0.4055. Okay, this is your delta value. Once we know this delta, I can use this formula for finding the zeta value. 2 pi zeta divided by 1 minus zeta square. Okay. Now I can take squaring on both sides. 4055 square is equal to 2 pi zeta whole square divided by 1 minus zeta square. Now we bring this denominator to left hand side. So if I simplify it further, 0.4055 square minus 0.4055 square zeta square is equal to 4 pi square zeta square. Now I can bring this negative zeta square term to right hand side and I can simplify. Okay. Yeah. So after simplifying this, I got the value as zeta is equal to 0.06. The zeta is nothing but the damping ratio. Damping ratio. Okay, already they mentioned in the question underdamped. So this value is also less than 1. Okay. So once we found out this damping ratio, I can use this formula. C by Cc. Cc is nothing but 2m omega n. I can use alternate formula for this. 2 root of mk. Okay. Our zeta value is 0.06, P unknown value, 2. Mass value is 5 kg into 5 into 10 power 3. Okay, now we will simplify this. .97 Newton second per meter. Yes, but they asked in nearest integer. So our C value is 19 Newton second per meter. Now let us move to the next question. The uniform prismatic bar of total mass m is suspended from a ceiling by 2 identical springs as shown in figure. Let omega 1 and omega 2 be the natural frequencies of mode 1 and mode 2 respectively. Here omega 1 is less than omega 2. Okay. The value of omega 2 by omega 1 is how much? So we have a rigid prismatic bar. They are suspending from the ceiling. Okay. In the first mode, it will oscillate along this direction like this. Okay. Equally it will move. It will oscillate like this, up and down. Okay. This I can consider it as mode 1. For mode 2, one side will come down, another side will go up. About the center point, it will oscillate. This we can consider it as mode 2. Okay. For first mode, this is K, this is also K. If I take this first mode, these two springs are in parallel combination. Okay. I can use the formula K equivalent divided by M. Okay, since it is in parallel condition, I can put direct addition. This is our omega n value, n1 value. Then we'll go for a mode 2. For mode 2, this is our theta value. Okay, this is our theta value. I can write down the equation of motion. Since it is rotating about the center point, so inertia torque is equal to restoring torque, or inertia moment is equal to restoring moment. I theta double dot. This is opposite direction. Resisting moment will be in opposite direction. So I'm using negative sign for that. K x into L by 2. Okay. Now I can replace this x in terms of theta as follows. Sorry. K L by 2 into theta. Okay, L by 2 into theta. When it is oscillating this much distance, so arc radius into angle, that is equal to x into the moment arm L by 2. Okay, this is the force, this is the perpendicular distance, moment arm. Okay, at the same time, for this rigid prismatic bar, when it is rotating about the center point, the polar moment of inertia formula will come like this: ml square by 12. ml square by 12. So we will simplify it further. ml square by 12 theta double dot. I can bring the right hand side terms to left hand side. KL square by 4 theta is equal to 0. Now we can do whole divided by ml square by 12 plus here already we have KL square by 4 into 12 . Now we can simplify L square cancel. The coefficient of theta is considered as omega, right? So this is for second case. Let me take omega n of second condition. The coefficient remaining is 3k by m. So root of 3k by m. Root of 3k by m. So here the ratio which they asked is omega 2 by 1. So here they mentioned omega n1 is less than omega n2. Okay. If you look this 2 value, you can able to understand. So root 2 is there. Here root 3 is there. This is 1.414. This is 1.732. So this concept is satisfied. Now we'll find out the ratio. Omega n2 by omega n1 is equal to 2k by m. So we can cancel this. Remaining root of 1.5 will be there. If you simplify 1.2, this is our answer. Let us move to the next question. Yes, that's all. I think I didn't do any mistake. If anyone found any mistake in the solution, please post it in the comment box so that we can rectify future. Thank you all of you.
If you like this video, please like, share and subscribe my channel to encourage me. Thank you.